highly honored to take this opportunity to welcome you all the national to you all national webinar entitled with New Trends in Mathematical Modeling. So first of all, I would like to acknowledge my deep gratitude to our esteemed experts who have accepted our invitation to preside over this webinar, thus make us feel honored with their being presence. So I'm also thankful to all the participants from the various reputed institutions for joining this webinar, for taking a keen part in this important program. So I would like to extend my gratitude towards our worthy principal, Dr. Arkituli, for encouraging us to conduct a seminar like this today. So I am again thankful to you, sir. Your kind support, suggestion, guidance given to us as when we require. So I just briefly talk about the topic. What is mathematical modeling? So mathematical model is a description of a system using mathematical concepts and language. The process of developing a mathematical model is termed mathematical modeling. So mathematical models are used in the natural sciences such as physics, biology, earth science, chemistry, and engineering disciplines are computer sciences, electrical engineering, as well as in non-physical systems such as social sciences, say economics, psychology, and political sciences. So mathematical models are used composed of relationship and variables. So relationships can be described by operators such as algebraic operators, function, differential operators, etc. So several classification criteria can be used for mathematical models according to the structure, like linear versus non-linear, explicit versus implicit, discrete versus continuous, etc. So mathematical modeling problems are often classified into black box or white box models according to how much a prior information on the system is available. So a black box model is a system of which there is a no prior information available. A white box model is a system where all necessary information are available. So practically all systems are somewhere between the black box and white box model. So this concept is useful only an intuitive guide for deciding which approach to be taken. So mathematical models are of great importance in the natural sciences, particularly in the physics. So physical theories are almost invariably expressed using mathematical models. So throughout history, more and more accurate mathematical models have been developed. Newton's law accurately describes many everyday phenomena, but at certain limits, theory of relativity and quantum mechanics must be used. So it is common to use idealized model in physics to simplify things. So this is the brief topic information. So we have assembled here to know more about the topic with many eminent speakers. So lined up to this seminar. So I would like to invite our worthy principal, Dr. Arkituli. So over to Dr. Arkituli.
Okay. Honorable guest, Dr. B.K. Das, Professor and Dean, Department of Mathematics, University of Delhi. Respected Dr. Om Prakash, Professor, Department of Mathematics, Guru Nanak Dev University, Amritsar. Respected Dr. Jitendra Singh, Professor, Department of Mathematics, Guru Nanak Dev University, Amritsar. Eminent scholar, honored guest, staff members, and dear student. It gave me immense warmth and great pleasure to grace all of your presence in this webinar entitled New Trends in Mathematical Modeling, organized by the Department of Mathematics of SSM College, Dinanagar. I am contented to see that many distinguished scholars and teachers have joined this webinar to share their knowledge and expertise from the country across the world: Philippines, Bhutan, Nepal, Nigeria, Bangladesh, Indonesia, Sri Lanka, Saudi Arabia, Malaysia, and Hungary. The seminar schedule brushes upon a spectrum of existing and befitting themes that discuss the recent trend in mathematical modeling. I would like to take this opportunity to express my deep appreciation for Dr. B.K. Das, Professor, University of Delhi, for honoring us as a keynote speaker for this webinar. I also wish to give special thanks to Dr. Om Prakash, Professor, Guru Nanak Dev University, Amritsar, and Dr. Jitendra Singh, Professor, Guru Nanak Dev University, Amritsar, for sparing time to grace the occasion Last but not least, I must also mention and thank the entire guest for being a part of this event. Now, I would like to have an honor to introduce our worthy guest, Dr. V.K. Das, a man of few words but great action. He is such a great personality who really need no introduction. He has been a great literary source in the world of mathematics. He has published over 100 research papers and edited 7 books apart from supervising 30 PhD candidate and over a dozen of MPhil students. He has traveled to the several countries for visiting scientists such as USA, Canada, Italy, France, Germany, etc. He has delivered more than 150 lectures outside India in these reputed country. He was elected as the president of Mathematical Science section of Indian Science Congress Association. He was the chairman of National Committee of Indian Mathematics years 2009 of Ministry of Science and Technology. He was also elected as the president of Academy of Discrete Mathematics and Application. He was also appointed as ambassador of ICM held in South Korea in 2014. Presently, he is a visiting professor in University of Automatic Technology, China. Last but not least, he is a man of unique, innovative bent of mind and epitome of numerous superb quality. I am also grateful to our other special guest of the day who spared his valuable time for this event. As today we have with Dr. Om Prakash, Professor Dinanagar University, Amritsar, who has an enriching research and teaching experience over 36 years to his credit. He got a number of awards for his excellence as he was bestowed with the Award of Excellence in the year 2009 by the Indian Society of Information Theory and Application for the contribution in the field of information theory. He has been a proud member of various reputed academic bodies. He has a good amount of research work to his credit as he has more than 100 publications in the various reputed national and international journals. His relentless endeavor have witnessed unparalleled success that keep us inspired to innovate and explore new way to secure a better future for our students. Dr. Jitendra Singh from the Dinanagar University is another gem with us who is regarded as a erudite in the field of mathematics. Besides being an academician of repute, he holds several academic administrative positions in the university. He traveled many countries across the world like China, United Kingdom, and Switzerland. He was selected as a UGC assistant professor in the mathematical sciences by UGC under the Precious Faculty Recharge program in 2015. He got visiting fellowship sponsored by the Royal Academy of Engineering, United Kingdom. He got travel grant by the NBHM to attend the International Congress of Industrial and Applied Mathematics in Switzerland. He has membership of various academic bodies like American Mathematical Society, Ramanujan Mathematical Society, International Association of Engineers. His leadership quality gives inspiration to the youth and is looked upon as a respectful teacher, accomplished academician, able administrator, and good human being. Today, we will have the talk of these scholars around the new trend in mathematical modeling on the behalf of my institution. I am compelled to this esteemed personality who raise the charms of the event with their benign presence. I would like to express my heartfelt gratitude to all of you who sincerely committed to this event to make it a success. I hope you have engaging, enriching session and it will be beneficial for your future venture. Thanks.
Thank you, Principal Sir. So I'm again thankful to you, sir, for your kind support, suggestions, and guidance given to us. So I again welcome all the worthy guests, Dr. B.K. Das ji, University of Delhi, Dr. Om Prakash ji from Dinanagar University, Amritsar, and Dr. Jitendra Singh, who's recently joined us. So without wasting too much time, I would like to invite our esteemed guest, Dr. Om Prakash from Dinanagar University. So over to sir.
Thank you. Esteemed Professor B.K. Das from Delhi University, my colleague Dr. Jitendra Singh, Dr. R.K. Tuli, Principal of this institute, teachers, friends, and my dear students. It is my great privilege to speak a few words on the webinar, New Trends in Mathematical Modeling. See, the main objective of teaching mathematics to the students of mathematics is to develop in them a habit of logical thinking and concentration for solving not only the mathematical problem in the classroom, but to develop in them a healthy mental attitude, enabling them to face the problem of their real life as well. The main purpose of this national webinar is to train our young scholars in the field of mathematical and computational techniques with a view to orient them in interdisciplinary research so that they can apply the knowledge thus acquired in other disciplines. This webinar would have a unique distinction of sharing the expertise of well-known mathematicians with the participants. On behalf of the organizing committee, I express my gratitude to the keynote speaker, Professor B.K. Das and Dr. Jitendra Singh, who despite their extremely busy schedule, have been able to make their expertise available at the webinar. The purpose behind organizing such academic activities like conferences, symposia, training institute, training programs, summer institutes, workshop, etc., is to boost the general awareness to spread mathematical culture across the country, to train our young scholars, and to abreast them of the latest developments in interdisciplinary subject so that they could take the benefit of the presence of the experts. Now, being a man of mathematics, I am proud to say that in the recent years and even in the past, mathematics has proved to be a backbone of science, technology, economics, and commerce. The development of an institution depends upon the quantum of mathematics available with the students and the scholars of that institute. And if I do not exaggerate, mathematics has been at the back of most of the scientific discoveries and has played a pivotal role in most of the Nobel Prizes in different disciplines of science, technology, medicine, economics, etc. Interdisciplinary mathematics, on the other hand side, is inherently applies applications of mathematics and its techniques in carrying out research developments and consultancy in other disciplines. While addressing the participants, I would implore upon them not only to acquire more knowledge of mathematics, I would again say not only to acquire more knowledge of mathematics, but also to disseminate their knowledge in an easy, interesting, and comfortable way. I'm sure with the support of all active researchers, the institution will make useful contributions to the development of this interdisciplinary subject. It has been observed that there has been a redundancy and overlapping in similar situations, which, if removed, can increase the efficiency of the system. The development of new mathematical models will definitely reduce uncertainty, which will help in increasing the efficiency of the system. While concluding, I submit that though many mathematical models have been developed, but still there is scope that many new can be developed, which will find tremendous applications in a variety of mathematical disciplines. I would say that a good teacher can only be a good researcher. And if you induce one young scientist in the field of mathematics, it will be your great contribution to the society and to the country at large. I'm sure that the present academic event will enable us to speed up our movement towards this noble goal. Since Principal Saab, academic atmosphere has been created in your esteemed institute, I'm sure the enthusiastic organizer will make all out efforts to sustain this atmosphere. Thank you all.
Thank you, Dr. Om Prakash, for your wonderful lecture. So you're more focused about the boost the young scholars towards the interdisciplinary course. So math is easy when we express it is in easy way. So I would like to invite our keynote speaker, Dr. B.K. Das from University of Delhi. So over to Dr. B.K. Das ji.
Okay. Am I audible?
Yes, sir.
Yes.
Okay. Good morning to everyone.
Good morning, sir.
Dr. Tuli, principal of this college, Professor Om Prakash, my old and dear friend, Professor Jatinder Singh, and Dr. Vishal Mahajan. At the very outset, I would like to congratulate you people to have organized such an important webinar,
Thank you, sir.
which is the need of the day. The topic which you have chosen is new trends in mathematical modeling. But before understanding, before knowing new trends, we must try to recall some of the old achievements as well. Mathematical modeling is a very vast term. In fact, it is believed that everything under the sun can be modeled mathematically. This is the general belief. I propose to share with you few mathematical models, not very recent, but of the past, like mathematical modeling and communication theory. I would discuss with you mathematical modeling and game theory, mathematical modeling and biology, and a couple of others also. So let me begin. Let me also tell you one thing, that this is my first online webinar, and I was not prepared. Otherwise, I could also have wear the suit and tie and all those things. I was becoming very casual, sitting at home and delivering a lecture. The first one, I have always declined because I never enjoy delivering a lecture online. This is my perception, maybe that it gets changed from today. Something which is really closer to my heart is the modeling, mathematical modeling vis-a-vis communication theory. I am trying to recall the year 1948-49, when a great scientist, not a mathematician, an electrical engineer, Richard Hemming, he was working in his laboratory, Bell Laboratories in America. He was confronted with a peculiar type of problem in his computer. Let me also tell you something, that there is a belief that computers came into existence in the year 1960. That is not a fact. Computers came into existence in 1960 for commercial use. But before that also, computers were available in big laboratories and for research purposes. So Richard Hemming was confronted with the peculiar problem that whenever he would run a program, then there would be an error in the outcome. Just one error in the outcome. That was something peculiar. Not always. The error will not occur always. But whenever there is an error, then it will be at a single place. And taking a clue from another scientist who is known as the father of information technology, Claude Shannon, Richard Hemming tried to rectify that problem by developing a mathematical model. And he developed a mathematical model by means of which he provided us the mechanism with the help of which that single error, whenever it occurs, could get corrected. And his contribution is known as Hemming's single error correction procedure. This is well known. And Hemming became popular overnight after when he threw this kind of an algorithm. Not because it was a theoretical model. Initially, the model was theoretical in nature. But he could implement that model successfully in his computer, by means of which he could control that single error. Not that error did not occur, error did occur, but he was able to correct that error. He developed a mechanism by means of which he was able to know if error has occurred, and if error has occurred, then he was able to correct that also. This concept found enormous applications worldwide after his researches, when they were published in the year 1950 in the Bell System Technical Journal, Single Error Correction Procedure by Richard Hemming. And one of the beautiful applications, there are so many, enormous number, I cannot mention all, but one of the beautiful applications which came later on of this procedure of single error correction was in telecommunication industry. In the telecommunication industry, again, mathematical model was framed, and the initiation was taken up by England, scientists of England. And in that team, there were a couple of mathematicians too. What they did was that, it is just, I'm trying to recall that some of you might had the chance to visit England. In the city of London, all the telephone numbers are of 10 digits. And with the kind of provision which Hemming had provided and implemented successfully, the situation has been that if you dial any number wrongly, any digit wrongly, or you misdial intentionally or unintentionally, even then you get connected at the right place. The condition was that all the remaining 9 digits should be dialed correctly at their respective places. So you were free to commit one error and still you get connected at the right place. Of course, the situation has changed in India now, but until a decade ago, we in India used to dial the correct number, and how it used to get connected, we all know that many a times that we are getting connected to a wrong place by dialing a correct number. But anyway, that was one thing which came as an application. We have been talking of and listening, reading, studying about this Nobel Prizes. We all know that Nobel Prizes were initiated by George Nobel in Sweden. And these prizes are bestowed only to one person, not in every subject, in few subjects. So George Nobel wrote in his will that here is a list of about 10 topics to begin with at that time, in which Nobel Prize will be awarded. In the second point in his will was the constitution of a committee, that the committee's constitution will be like this, that so many people will be there from different walks of life. Third thing which he wrote in his will was that this list can be amended. Some of the topics may be deleted or added after every 10 years. And let me just tell you that the changes have been made only 2 times up till now. And the final dictation which he wrote in his will was that mathematics has to be kept outside this race. So there has not to be a Nobel Prize in mathematics. And this is but natural that when such kind of things happen and people came to know of it, mathematics was never brought in the ambit of Nobel Prizes. Then many kinds of stories got coined up. And one of the most prevalent story was that the wife of Nobel was in affair with a mathematician. And that was the reason, because Nobel knew that in case if mathematics is included, then it is that fellow who is going to be bestowed with the first Nobel Prize in mathematics. He knew about it. But you see that mathematics is not a subject which can be bound by these kinds of awards or prizes. The role of mathematics, the strength of mathematics, the power of mathematics was not hampered by non-receipt of Nobel. In fact, mathematics helped many other branches in the academic fields. Because of that, people fetched Nobel Prizes. And the first in this category was John William Nash, who died only about 3 years ago in New Jersey with his wife in a car accident. And John William Nash was the person who was basically an applied mathematician. He had developed few game theoretic models. We all know that game theoretic models are in continuation to linear programming models, which we all teach at graduate level as well as at postgraduate level. So in game theory, he developed several kinds of models. This was purely a work in applied mathematics. But coincidentally, some of his models, they found applications in economics, particularly in agricultural economics. And because of those applications in agricultural economics, John William Nash was bestowed with the Nobel Prize in economics for his contributions mainly in applied mathematics. So mathematics helped to fetch Nobel Prizes in other fields. And I may just add that John William Nash was much later on bestowed with the Abel Prize as well in mathematics for the same contribution which he made, on which he was awarded this Nobel Prize. Because Abel Prize is given to a person working in mathematical sciences. So the only fellow, the only scientist who has been bestowed with these two most prestigious awards. So he had basically modeled the concepts of game theory in modeling. This is what he had done. There are many more applications of these game theoretic models, particularly Nash equilibrium model, deterministic model, non-deterministic model, statistical, non-statistical. So there are so many. Another modeling which developed in the field of biology was due to some kind of a blunder which was committed by the scientific administrators of this country about 4 decades ago. When this 10+2 scheme was introduced in the country, then at that time, students were given the option at +2 level to go in for a medical stream or non-medical. And many students used to opt for medical stream because in case if a student chooses medical stream, then the candidate will not have to study mathematics. So people joined medical group, but without knowledge of mathematics at that level. They grew in the field of medical sciences ultimately. India had the best of doctors in every field, in every discipline of medicine. We could produce, but they all or most of them lacked in research in biology. In case if you just turn over the pages of a couple of medical journals like Nature, you will not understand, because we are all mathematicians. We will not understand the biological part. We have just to turn over the pages. Then you will see that how mathematical this biology has become. And when this kind of a mistake was realized at the government level, then about 12 years ago, the government of India decided to establish some kind of a platform where mathematicians and medical scientists could interact with each other. And the first effort in that direction was to have thought of establishing some kind of center for mathematical biology. I was coincidentally chosen to be a member of that commission, which was to work out on the possibilities of establishing this kind of a center. But the problem was to look for an institution in the country where this could be established. The committee identified several institutions on their own because most of the members in the committee were mathematicians. And we started our exercise by exploring the possibility at Indian Institute of Science, Bangalore. And we had a 4 days marathon meeting with people of different disciplines, with mathematicians, with people of molecular biology and others. And we were shown several kinds of demonstrations. We were in a fix as to whether we are in a position to give our note to establish Center for Mathematical Biology at IISc, which is one of our prestigious research institutions, or not. When we were being shown several kinds of demonstrations, then during one of the demonstrations, what we had noticed was that when brain cells were cut into slices, this was a demonstration which was shown by people of molecular biology, that when brain cells are cut into slices, then this procedure gives rise to several fractals several differential equations, several configurations. And to solve those kinds of differential equations are really challenging. That's a real challenge for mathematicians to solve. Even as on today, many of the equations could not be solved completely. What I'm trying to say with this is that it is not that mathematics has helped other disciplines to grow. Even other disciplines have also supported mathematics to grow. And that was the turning point where we took the decision to establish first Center for Mathematical Biology in the premises of Indian Institute of Science, Bangalore, which is still functional. The convener, the main person responsible for that center was Professor Rangarajan, who has taken over as director of IISc Bangalore. My visits to China, I'm talking of the current mathematical models now. I am coincidentally visiting professor for 3 years at Hubei University of Automotive Technology. You can have a feel as to what a mathematicians will be doing in the University of Automotive Technology. Not that they got a dream to ask me to join them. This was on the basis of interactions with those people in several committees, international committees, in meetings abroad. And then they identified two problems. Now, please note as to how mathematical modeling is going to help. They had identified two problems. Most of us, we drive our cars, and the latest cars are dependent on different kinds of sensors. And in case if a sensor fails, the car stops. This is what is happening unless you get the sensor changed. This was the problem which was identified by that University of Automotive Technology to develop some kind of a mechanism which is parallel to that of inverter. That can we fix up some kind of a device in our cars so that whenever any sensor fails, then at that particular moment, the car does not stop. It gets changed automatically to the new sensor, and the process goes on, and whatever rectification is to be made, that can be taken care of later on. And since I know about these topics on artificial intelligence, networks, sensor networks, and all that, so this was one of the problems which they shared with me in Hong Kong during one of the meetings. And another problem which they shared with me was the designing of the frontal shield of the car. When we drive our car, because we have right-hand drive, the steering is on the right-hand side. And when we drive the car, then maybe that you might also have noticed that there are some kind of a hindrance towards the right side of the car with the kind of shield and other metals which are fixed over there. And that university made this exercise and found that nearly 5 to 7% of the car accidents, they happen because of that kind of a hindrance. This is what they had noticed. So this was another problem which they had identified as to how can we or can we redesign the shape of the frontal view of the car without compromising on the strength of the body of the car. So these were two problems which were identified, and I was asked to visit their university. We had some kind of a interaction between the experts in that university and myself for about a week's time. And ultimately, I gave them my node. They wanted me to settle in China for 3 years. Thank God I did not get settled at that time. I took the right decision. Otherwise, people of India would have cursed me. So, but I continue to be working online with them on these two kinds of problems. So, our aim is to develop mathematical models, some kind of mathematical models with the help of which we could redesign the frontal look of the car. This is what we are doing. One of the latest activities which I have joined is regarding this COVID-19. This is a much sought after thing because this pandemic has created a havoc. This has brought revolutionary changes even in the field of academics. We have learned studying our subjects, attending the schools, attending the universities, without going to the actual classroom, without making use of blackboard or whiteboard. And we have become used to this kind of an online, and this perhaps suits to the government also. They think that why to hire so many teachers in the colleges and university, and the popular lectures can be recorded and can be transmitted to all the institutions. One of the roles of mathematics people, how mathematicians have been able to help and they are helping in this era of COVID-19, is by making use of artificial intelligence and machine learning. These are the two essential tools which help in the prediction analysis of COVID-19. It tells us about the intensity of COVID-19 at different places in different atmospheres. It helps in showing the trends with the help of pattern recognitions, which all of us as applied mathematicians can help. And this is what we have been helping in this era. You'll be surprised to know that we all drink this coconut water, and after drinking this water, we throw away this skull of that coconut. And you know that that south of India is the largest producer of these coconuts. So all of the skulls of the coconuts are being dumped somewhere near the sea, or they are thrown in the sea and all that. There was a committee which was constituted by Ministry of Science and Technology, not to look after only this aspect, but to look into several kinds of proposals which could enhance the livelihood of SC, ST, and tribal communities. And we found that these coconuts, we just made a survey as to why near the seashore all these skulls of coconuts are being assembled, being put up. And later on, we found that all of them were being picked up. All of them were picked up by Japan and South Korea. They were taking those skulls of coconuts as shiploads, and we were happy that we have not to throw them in the sea. They used to pay to our laborers who used to be in Tamil Nadu, belonging to all these categories. So after an exercise of a year and a half, we could find out and determine as to what they were doing with these skulls of coconuts. With the inside of these coconuts, which is a soft part, ropes are being made even in India earlier also. There was nothing new about it. But from the outside skull, which is hard, they were manufacturing bricks. And believe me, that those bricks were light in weight. Those bricks were 10 times stronger than the bricks which we are using. So this kind of survey, when we came to know of, then we tried to set up the first center in Coimbatore, where we could hire about 8 to 10 people belonging to this category, and we could set up the some kind of a mini industry, we can say, with the help of which we had also started manufacturing these bricks. And this was, now the question is that where is mathematics in this? You see, those skulls were broken into pieces, but it is the mixture which used to help us in making those bricks was to be mixed up in a particular ratio and proportion. And herein, with the concept of ratio and proportion, comes the concept of this mathematics. Mathematics was known to be queen of all sciences until few years ago. But nowadays, mathematics is known to be mother of all technologies. In case if you survey with the parents of +2 children as to which kind of career they would like to choose for their wards, then they would say that engineering or medical science. Nobody would talk of basic sciences. Another jerk which was made was because of the development of engineering, mushroom growth of engineering institutions in the country, because they started using mathematics as a tool. Mathematics departments were only the service departments for them. They never allowed mathematics people to grow. And let me tell you, my friends, that this technology is important. Basic sciences are equally important. This is just like the example of bread and butter. Technology is like our bread. Technology is like butter, and basic sciences are like bread. It is possible to survive on bread alone, but not on butter alone. So in case if we want to carry out and develop good models in mathematics, then we shall have to rise above the level of theorem proof, question answer, problem solution. So we shall have to change our mindset like that. And I'm sure that in case if we start thinking of mathematical concepts beyond these things, then certainly we are going to serve the cause of mathematics as well as the human mankind. Now, before I close, I would like to quote the saying of one of the greatest philosophers of India, Dr. Sarvapalli Radhakrishnan. This is in the context of whether we can do or not. Dr. Radhakrishnan was president of India when the demise of our second Prime Minister of India, Lal Bahadur Shastri, took place. And everybody knows that he was a very simple man. And Dr. Radhakrishnan was asked to make a comment on his sad demise. And Dr. Radhakrishnan said that sincerity is better than ability. So, in case if you have a sincere approach, then ability does not matter. It comes as a logical outcome of that. So, you have to be sincere into that. And with these, I must thank the organizers of this webinar to have given me this opportunity and allowed me to have shared my thoughts regarding mathematical modeling. So without taxing your patience anymore, I would like to say thank you very much. Thank you.
So you told that this is your first webinar, but sir, we really enjoy. We all are enjoy your webinar, and you have no need to prepare, sir, because you are the source of the knowledge for us. And you also talk that George Nobel write his will that Nobel Prize is never given to any mathematician. And but sir, you also talk about that mathematics is a mother of all technologies. So I add something. I add something that mathematics is a queen of all sciences, sir. I'm right, sir?
I said that mathematics, which used to be known as queen of all sciences, is now mother of all technologies.
Okay, sir. Right, sir. We really enjoy your lecture, sir. So thanks a lot. So now I would like to invite Dr. Jitendra from Guru Nanak University, Amritsar. So over to Dr. Jitendra.
Hello, am I audible?
Yes, sir.
Okay, thank you, Dr. Vishal. Before I proceed, first of all, I would like to thank uh, Professor Tuli and my senior colleague, Professor Om Prakash, for inviting me for this webinar. My gratitude towards Professor B.K. Das for this wonderful talk, and also for my senior colleague, Professor Om Prakash and Dr. Professor Tuli. Yeah, as from the talk of Professor Das, all participants, you might have enjoyed the talk because from the very first word I was listening his talk, and it was, it was wonderful to hear him, and so many aspects he has touched upon regarding new trends in mathematical modeling. However, I have been told that uh, I should prepare something too simple to so that in mathematics, so that people, our participants, can enjoy it and understand well. And I will not be discussing anything about practical applications of mathematics, but somehow you can say that I will talk about uh, mathematical modeling while sitting in mathematics itself, sort of for this thing. So the title on which I would be speaking in is this one. So let me share my screen first. Is it visible?
Yes.
Okay, so the title is An Axiomatic Approach to Circular Functions. And I think even our undergraduate students can well understand the meaning of circular functions because they are known to everybody. Whether you are working in pure maths or working in applied maths, all of us come across the elementary functions, and circular functions are among them, right? So I start with this problem. So the problem is prove that limit this well-known limit sine x over x is equal to 1 as x approaches 0. All of us know that this limit is equal to 1. And if you come to the proof, then we know that the proof is either geometric. You take the circle and work with the radian definition of angle and go ahead with the approximations, and you get the limit equal to 1. Or you can use the infinite series representation of sine function. These two things you can utilize in order to prove that this limit is going to be 1. But we know that you cannot utilize this Hospital rule to evaluate this above limit. You cannot take it lightly because you have, if you evaluate the derivative of this sine x, what happens? Uh, in the calculation of this derivative of sine x, within this simple calculation, you counter this limit, right? Because, so in other words, if you want to calculate the derivative of sine x, then this above limit is involved. So you cannot utilize the Hospital rule because that involves derivative of sine x. So what would you do if you are asked not to utilize geometry or not to use the infinite series representation of sine function, because infinite series representation is far vast thing for a fresh calculus student to start with. So what is the alternative then? So we will try to model the definition of, I mean, in other words, in the sense that we will try to provide you another definition of sine and cosine functions, but this time without using geometry and without using the infinite series representation of such functions. So this is the theme of my talk today.
ठीक है हाँ बिल्कुल सही
So we have this result that due to Professor Robinson, which was published in Mathematics magazine. It's a beautiful paper, and I have picked up material from this paper. So suppose we have a positive real number p, and s and c are two functions from R to R, which satisfy these three axioms. The first one is they are familiar axioms: cx minus y equal to cx cy plus sx xy, and we assume that the s at p is 1 and s is non-negative on the interval 0 to p. Then the result says that these functions s and c are always uniquely determined. So what do we get from this theorem? That if we take our p to be equal to pi by 2, then s and c, our sine and cosine, these are precisely our sine and cosine functions respectively. So if somehow we can prove this result without invoking into geometry, then or infinite series considerations, then we have the luxury of defining sine and cosine functions without circling. So let's see what we can do. First of all, we will try to prove several facts based on these three axioms being satisfied by the two functions s and c. So we need to keep in our mind that first axiom is cx minus y equal to this much, and s at p is 1, and sx is bigger than equal to 0 on the interval 0 to p. So starting with these three axioms, we will deduce a few things. So let's see what we can deduce out of these three axioms first of all. So first one is we can show that c at 0 comes out to be always to be equal to 1. So, and we are allowed to use only those three axioms, which I have stated already. Cx minus y equal to cx cy and plus sx sy. So you use the first axiom. So you start with c0. You can write this cp minus p and apply it here. So what do you get? You get cp square plus sp square which comes out to be equal to, because SP is equal to 1, so this is equal to something non-negative plus 1. So therefore, this shows that that C0 is bigger than equal to 1. C0 is bigger than equal to 1. Now, on the other hand, if you see C0 again equal to C0 minus 0, so again apply the first axiom. What do you get? C0 square plus CS0 square. So which is sum of two non-negative numbers and which is bigger than equal to one of the numbers, right? Each number, that is C0 square. So therefore, C0 is bigger than equal to C0 square. Since C0 was already bigger than equal to 1, so we can cross out C0. So what do we get? So we get 1 greater than equal to C0. So simultaneously, C0 is less than equal to 1 as well as greater than equal to 1. So therefore, C0 must be equal to 1. Not only this, you can immediately prove that C is an even function of x on R, that is C minus x is equal to Cx, just by using those axioms. So go ahead with the first axiom once more. You consider C minus x equal to C0 minus x and apply the axiom 1. What do you get? C0 Cx plus S0 Sx, which is equal to, which is same as, so if you apply this one, Cx minus 0, again you are getting the same expression, whether you take Cx minus 0 or you take C0 minus x, right? So that way, this shows that Cx is equal to C minus x. So look at the difficulty level here. I think everything is much easier to prove here without looking at any figures or something like that. So without geometry, we are able to construct these proofs. So the next one is Pythagoras theorem. That is Cx square plus Sx square is equal to 1. That just becomes a trivial thing now, because you have the first axiom again, 1 equal to Cx minus x, and which is nothing but Cx square plus Sx square. But with a caution, because right now we don't know whether S and C, these functions are sine and cosine functions or not. So this is some sort of Pythagoras theorem, but not exactly the same which we usually talk about. Okay, so it will depend upon the number P which is involved in the definition of in the statement of the theorem. So in the similar way, now you can establish that this S function always have these bounds between 0 and 1 on the interval 0 to P. So for this one, so this has already been given to us as from the third axiom that S is greater than equal to 0. For the other part, you can proceed by considering this one, the Pythagoras theorem as proved earlier, Sx square less than equal to Sx square plus Ex square, and this amounts to equal to 1. So this shows that S, and since S is non-negative, so therefore S has to be less than equal to 1. Similarly, if you want to prove that S0, so see here also S0 is equal to P is going to be equal to 0. So you can proceed again the same way. So you can start with Pythagoras, consideration of Pythagoras and the fact that we have C0 is equal to 1. So you have 1 plus S0 square is equal to C0 square plus S0 square, which is equal to 1. So this shows that S0 is equal to 0. And using again the Pythagoras theorem, this time for x equal to P, you can get that Cp is equal to 0. Okay, so these elementary things, not only this, you can prove almost everything regarding trigonometric simple formulas, I mean the fundamental formulas. So what about this one? Cp minus x comes out to be Sx. And P was just assumed to be a real number, positive real number. So you are getting here applying the same formula, Cp minus x, the first axiom that amounts to Cp Cx plus Sp Sx, which is equal to Sx, because Cp was proved to be 0 and Sp is equal to 1 by axiom 2. Similarly, you can show that Sp minus x is equal to Cx, because you can write Sp minus x to be equal to this one, which is coming out to be equal to Cx. So how simple it is, you can understand this. Then similarly, Sp by 2,
Hello.
you can prove that this is equal to Cp by 2. And then the part D. Part D is that C lies between 0 and 1. It is also assumed because our function, you can write C to be equal to SP minus X on 0 to P. So therefore, C lies between 0 and 1. Now you can, proceeding the same way, you can prove that the S of X plus Y is equal to this much, and S2X is equal to 2SX CX. So again, you can utilize these formulas, early established formula along with the axiom 1 to proceed for this one. And these simple calculations, you can just see that the proof of a part A of 7th remark, and similarly part B follows from part A easily, because you can take X equal to Y there. Okay, so similarly you can prove the this familiar formula that 2 times CP by 2 square is equal to 2 times SP by 2 square is equal to 1, using these simple notions. So okay, so let me skip this part. So we are here now at the 9th remark. So for the 9th remark, we can see the very first one is SP minus P by 2 is equal to minus SP by 2. So the minus sign will come out, and then SP minus P is equal to minus 1, C2P is equal to minus 1, and finally using ABC, these 3 parts, one can prove that S is an odd function, that is S minus X is equal to minus SX. And every time we are using the earlier established results based on the axiom 1, axiom 2, and axiom 3. So this can be achieved easily because you have this one S minus X can be written as this much, and you can one line prove that S comes out to be an odd function of X on R. Okay, fine. The next thing is similarly Cx plus y, you can prove that this is equal to Cx Cy minus Sx Sy, using the fact that S has now been known to be odd function of X. So here you can utilize those formulas, expand using axiom 1, because C is even function. So therefore you can expand, you can write this to be SC of X plus Y equal to C of minus X minus Y. And then you can, what you can do is you can just use this one, right? So this is C of minus X, C is odd even function, so Cx, and then S is odd functions, so minus Sx. So you can just easily see that the formula holds, and B and C follow from the part A the same way. Okay, so next is remark is this sequence of formulas uh, S of X minus Y, this one, S of X minus Y equal to this much, S of P plus X is equal to Cx. These are good exercises for our students as well. C of P plus X equal to minus Sx, we can prove using earlier established results. Then comes S2P plus X equal to minus Sx, C2P plus X equal to minus Ex, and then finally F and G. Look at the F and G. S4P plus X is equal to Sx, which shows that S is actually a 4P periodic function, and C is also a 4P periodic functions. So we have what did we prove till now? So let's see. Let's revise what we did till now. We have yes. So we have C and S are 4P periodic functions on R. First thing this we have proved now, and then C is even, S is odd. So therefore, C and S are uniquely determined if they are uniquely determined on the interval 0 to P. So we look forward to prove that C and S, these functions are uniquely determined on the interval 0 to P. So let us define then them uniquely on 0 to P. So first thing regarding this is the fact that C is non-increasing function on 0 to P. So to prove that C is non-increasing function on 0 to P, we first notice that C and S both lie between 0 and 1. Both lie between 0 and 1 on interval 0 to P. And And not only this, we can see now that for all x and y in 0 to p, such that x plus y belongs to 0 to p, we can write here using the formula c of x plus y equal to this much, and utilizing the fact that s and sx sy are non-negative here, and c and cx cy are also non-negative. So you can this quantity is minus negative, so this is less than equal to cx cy, and which is less than equal to cx. So this shows that c becomes non-increasing function on 0 to p, and then using this fact, you can prove that s is a non-increasing function on 0 to p. So for this, you can utilize the formula which we have established already, c of p minus x is equal to sx. So whenever x belongs to 0 to p, p minus x also belongs to 0 to p. So this establishes that s is non-increasing, it should be non-decreasing function on 0 to p. Another one is for any constant c, remark 13, which we will utilize later on. Suppose cx is bigger than or equal to 1 minus c. Then c of xy2 is also bigger than or equal to 1 minus cy. So this calculation also follows, because cxy2, c always remains between 0 and 1. This is bigger than or equal to cxy2 square. So you can utilize the earlier established formula, some sort of double angle formula. So, and you can use the inequality, this one, because cx is bigger than or equal to 1 minus c. So utilizing it, you can immediately get that cxy2 is also bigger than or equal to 1 minus cy. And using this fact, you can inductively prove this important inequality. Cp by 2 raised to power n is bigger than or equal to 1 minus 2 raised to power n. Because Cp is equal to 0, which we can write 1 minus 1, right? So, and you can use induction afterwards to prove this fact. And why this fact is important? Because using this fact, we immediately discover that the sequence of real numbers, Cp by 2 raised to power n, this converges to 1. Limit n approaching infinity, C of p by 2 to the power n is equal to 1. Okay, so you can just consider this as an exercise, because this is this follows from B immediately, because C lies between 0 and 1, and we have this inequality with us, right? So you can use the definition of convergence accordingly. These simple notions now lead to the following fact, that C and S are continuous at 0. And to our students, undergraduate students who are fresher in calculus, how do we proceed for the proof that S function is continuous? I think that in any undergraduate course, usually in colleges, no one bothers about proving these facts. People just assume that S and C are continuous, so therefore we just proceed for the limit of those things and forget about other things. We never bother to prove that S function and C functions are continuous. Actually, we always assume them. So, so here with these simple notions, we would be able to prove that this both C as well as S are actually continuous at 0. So suppose that then that
ऑन हो जाएगा, फिर मेरी ऑडियो वीडियो दोनों हो जाएगा।
हाँ जी, आपका डाउन हो गया ना,
आवाज भी आएगी।
Okay, so epsilon greater than 0 is given to us, and we have already proved the fact that this sequence converges to 1, Cp by 2 to the power n. So therefore, by definition of convergence, we can find out an index n such that we have these are satisfied, 0 less than equal to 1 minus Cp to the this thing less than epsilon, right? For n greater than equal to n. So what we can do is we can take delta to be equal to p by 2 to the power n. So because we want to find out a limit, we want to prove that a limit of C as x approaches 0 should be equal to C of 0. This would mean that C is continuous, right? So we take delta to be equal to this much, and for all x mod less than delta, this implies that using the fact that C is non-decreasing, so non-increasing, so we have Cx to be bigger than or equal to Cp by 2 to the power n, and this proves that 1 minus Cx is equal to C0 minus Cx, which is less than or equal to this number, and which is already less than epsilon. Which is already less than epsilon, right? So these simple calculations prove that the limit of function c as x goes to 0 is equal to c of x. Similarly, you can prove this by using this relation that some function s is continuous at 0. So we are able to prove that s and c are continuous at 0, right? Now 14 remark is sufficient to prove that s and c are actually continuous functions. So they are continuous everywhere on R. So also, for this you can utilize the fact that s and c are continuous at 0. So therefore their limits are already known to us. So and use the formula and algebra of limits to deduce that uh, that this limit of sx plus y as x y goes to 0 is equal to this much, which is nothing but sx. So this proves that function s is continuous in the same manner function c is continuous. So look here, we started with 3 axioms and we are able to prove many more things about the properties of s and c based on only those three axioms. So let's proceed what we can do further. Now, I will not indulge into the proof here, but I will just let you know about what we can prove easily again. These the S and C functions are uniquely defined on 0 to P. So this is the final thing which we wanted in order to prove the theorem which I asserted in the very beginning of this talk. These function S and C are uniquely defined on 0 to P. So you remember that that a function is defined. Suppose we have a continuous function on an closed and bounded interval, then it is completely determined by its values on a dense subset, right? So what we will do, we will construct a dense subset, and on that dense subset we will prove that this S and C are uniquely determined. So therefore we are through. So for this we we take the help of induction and the formulas established so far. So we will use those formulas. We have ckx equal to, use this sum formula cx plus y, so that you are left with this one. And we also have cxy2 square is equal to this much. And these two formulas, starting with these two formulas, you can use induction in order to prove that ckx and cxy2 to the power n. These two numbers are known to us whenever cx is known to us. Okay. So after proving this fact, what we can see is, since we know already that c at p is 0, we have proved in the beginning that c at p is equal to 0. So therefore c at p is known to us. So therefore the value of cx for x of the form this kp by 2 to the power n in 0 to p is also known to us. So that means that value of c at this particular value of x is uniquely determined. And then the set, now consider this set D to be composed of all such numbers. And this is a dyadic set, so this is straightforward using the Archimedean property and something like that. You can prove immediately that this set is actually dense in 0 to P. So since it is dense in 0 to P, so and we have uniquely defined our function C here on this dense subset D, so therefore C is uniquely determined because C was already a continuous function. We have proved it earlier, right? Similarly, since function S can be expressed in terms of C, a composition of two continuous maps, so therefore we have got S to be uniquely determined, and with this we are able to prove the theorem which was stated in the very beginning. Okay, so what did we learn from this? That of course we can derive almost all properties, not only almost, but actually all properties of the function C and S once these functions satisfy these three conditions. The first one, second one, and third one. But did we really get rid of geometry after defining all this? Because of course, as I stated earlier, that when we take p equal to pi by 2, these functions are precisely the usual sine and cosine functions which we study in our calculus or in our elementary courses. But not really. We are not able to get rid of geometry at the moment, because what is pi? Pi is generally defined geometrically. So pi is involved in these definitions, right? If we take p equal to pi by 2, then only these functions they reduce to the ordinary sine cosine functions. So how to model this pi now? So we want the definition of pi which should be independent of the geometry, which should be independent of circle, because circle involves pi. It involves pi, right? But before this, we need to know one more thing, that that is pi actually a constant? How we will prove that pi is a constant? So we have yeah, this one. So we have how do you know that pi is a constant actually? So this, you can take the help of calculus right now to, in order to prove that pi is actually a constant. So for this, we have, all of us know that we can take a circle and of radius r, and proceed for this using integration, Riemann integration, to calculate its area and perimeter. So what are those things? So you can express a perimeter as well as area as integral, right? And we have a change of variable that lets us land here, p equal to this expression, and a equal to this expression, which involves some constants, right? So the blue one, I'm calling this as c1, and the red one, I'm calling this as c2. All right. So we claim that c1 is actually equal to c2, and this can be proved in elementary way. Look at those expressions. You can just use the integration by parts. So integral from 0 to 1, square root of 1 plus 1 minus x square. You can just see that this is going to be equal to this pink integral, and using this integral further in the blue integral at the last line. So what do you get? You get this to be equal to the sum of two integrals, and which is therefore, using the above pink integral, this is going to be equal to 2 times the integral, red integral, right? So now you can immediately discover that c1 is actually equal to c2. So this proves that c1 is equal to c2. Therefore, there exists a constant for which the perimeter of the circle is 2 times that constant r, and area is that constant times r square. So we can call that pi. But the problem is that our target is to obtain pi independent of circle. And here in this calculation, although we are able to prove that pi is actually some constant, but the thing is, we are using geometry here, right? And our aim is to get rid of geometry somehow. So let us proceed further how we can get rid of geometry. So for this, of course, if you want to get rid of geometry, you have to work harder, a little bit more, but the things will be, calculations would be easy. So we have this theorem that let S and C be as before, and take P equal to 1, and take f of x to be equal to Sx over x on the interval 0 to 1. And so this semi-open interval 0 to 1. Then one can prove that f is actually a decreasing function on 0 1. F becomes a decreasing function on 0 1. That too can be proved easily. It's not difficult, but I will just show you a little bit. But I will not be able to read out all of the proof. But I can give you the idea that if you take any real number within the interval 0 to 1, such that, and a natural number such that n times that real number is less than or equal to 1, then using induction, so you have a very good tool with us, induction. Using induction, you can prove these inequalities, that at least f increases, f is decreasing in this sense. F is increasing in this sense. F of x is less than, f of 2x is less than, and so on. F of x, f of nx. Okay, so now if you take 2 points x naught and y, what you can do is you just try to convert the things to bring x naught and y in such a way that x should be some natural number times some real number, and y should also be some other natural numbers times some real numbers. Say the real number should be same. If you do this thing, then you can compare those numbers applying the definition of continuity of the function f, because s was already proved continuous, and the identity map is already continuous. So therefore, this quotient is continuous. This continuity will automatically prove that f is actually a decreasing function on 0 to 1. Now, since f is a continuous decreasing function on 0 to 1, therefore its limit will exist. So therefore, this enables us the following result, that limit x going to 0, f of x exists. And proof is again easy here. The idea is that you inductively prove these two inequalities. If you prove these two inequalities, you are able to show that this sequence of numbers f of 2 to the power minus n, this is actually convergent, because a strictly monotone bounded sequence is convergent. So therefore, so we will get that this converges, and using the convergence of this sequence as we did earlier, you can immediately discover that the limit x going to 0, f of x exists. This proves that this theorem, again in a very elementary way. And now we have the luxury to define what we wanted. Here we have the following definition, that our number pi is equal to 2 times the, so let us, we are defining it now without using any geometry, that pi is equal to 2 times limit x going to 0, f of x. So therefore, pi can be defined without circle. But the thing is, remember that the way we have defined pi, this should come out to be the same pi as is usually known to us. Then only this makes sense. So to make this sense, we have to define sine function now. So we define sine function to be, once we define this pi, because limit x tending to 0, f of x exists, so therefore pi is there. So we define sine function to be equal to the s function, which we were considering earlier, s of 2xy pi. So rescaling of s function, and c function, cosine function, also the rescaling of c function. Okay, then the definition of pi, which has been given right now, which is independent of geometry or circles. So it matches with the one which we usually, because of the uniqueness of s and c functions, right? So which we have from the very beginning, theorem stated at the very beginning. So now what do we get out of this? First thing we got is that we have axiomatized the usual sine and cosine functions without considering any type of geometry. And second thing is that we started with this theorem in the very beginning as a problem that prove that limit x going to 0, sine x over x is equal to 1. So what we get out of this is that the proof of this theorem is now becomes trivial, and it does not use any type of geometry or infinite series. Look at the proof here. You can write 1 to be equal to 2y pi into pi by 2, which is equal to 2y pi, and pi by 2 from here is the limit sx over x, because f of x was equal to sx over x, last line. So this is further equal to, you can rescale this because x goes to 0, therefore 2ty pi also goes to 0. All right. So now what you can see is you can apply the definition of sine function now. This is equal to finally limit t going to 0, sine t by t, and this is equal to 1. This proves this fact. So by this talk, we have learned this thing, that we can completely axiomatise our definitions of sine and cosines, though these things actually appear in geometry. But we can do this thing independent of geometry. And one more thing I would like to emphasize is that throughout these proofs, so many things we have proved without drawing even a single diagram. So we have just relied only on 3 axioms which were given in the very beginning.
Dr. Jitendra Singh?
Yes, sir.
Come to back. The function you have taken fx,
Yes.
This has the unique limit.
Yeah, limit is always unique once it exists.
Then the value of pi will be fixed.
Yes, of course.
It will be fixed one.
Yeah, it's always fixed.
It is fixed, and what is the how will be approximated?
So see, f of x, once we limit, we have got the limit, and we have defined s and c functions, right? We can approximate in the usual way.
Acha.
Because it matches with the pi, which was geometric pi. So with
But
this definition,
how much different is than whatever we take 22 over 7 or like that?
Oh, a lot of differences there, because pi is actually irrational and this is not. So
Acha.
this is a rational number. So actually, what we have done is pi is already there, but it was geometric earlier. So without using geometry, we have defined another number. You can call it something else. You can call it, maybe you can call it as pi 1. Now we claim that pi 1 is actually equal to pi.
Right. It is very interesting topic.
Yeah. So everything which we have done right now is independent of geometry here, because in our perception right from the beginning of our calculus course, or maybe +2 plus standard or 10th standard, we were used to taught that that these things are geometric representations, but these are not. So this can be axiomatized. This is what was the theme. So so I hope that this will fit into the mathematical model while sitting in mathematics in some sense.
Have you thought of some other functions who can be proved without this trigonometric techniques?
Yes, yes, of course. So now one can proceed for the identities obtained for the tan and cotangent functions, secant and secant functions. You can always try to define them independently of these sine and cosine functions. The same way,
Right.
and not only this, you have exponential function with us. Again, exponential functions we define it in a very horrible way. But again, exponential function can be given the same treatment. Again, you can start with 3 axioms, and you can prove everything about exponential function. Not only this, a logarithmic function as well.
Right.
So these things can be, generalized to sine and cosine. Other functions as well. Not all, but the very fundamental ones: exponential and logarithmic function.
Okay.
So whole of the trigonometry, you cannot now. You need not to say that the trigonometry is only the part of geometry. So trigonometry can be considered a part of algebra and analysis.
Right.
Yeah.
Okay. It was very interesting lecture. Thank you very much,
Thanks.
Dr. Vishal.
Thank you very much. Your lecture is
Dr. Vishal, you're not audible.
Yes.
yes, I'm audible, sir.
Right now.
So on the behalf of SSM College Management and all students, I would like to extend my heartiest thanks to our honorable guest for their presence in this function. So thank you for enlightening us with your inspiring and motivating words. So you are an exemplary personalities, and we have a lot to learn from you. Last but not least, thank you to the organizing committee and the volunteers for their tremendous contribution to make this event successful and enjoyable. So thank you everyone once again for your gracious presence. Thanks a lot. Thank you very much.
Thank you.